lecture, I would like to say Einstein quotes, "Imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution." Students, let us begin today's lecture with a short question. What are the relative terms in physics? What is Newtonian relativity? What are Galilean transformation equations? What are the failure of Galilean transformation equations? Einstein's special theory of relativity, derivative expression for Lorentz transformation equations. Consequence of Lorentz transformations, namely length contraction, time dilation, simultaneity, velocity addition, etc. A well-defined coordinate system which can explain the motion of objects is called frame of reference. There are generally two types of reference systems: inertial frames or unaccelerated frames, non-inertial frames or accelerated frames. A frame of reference is said to be inertial when the objects in this frame obey Newton's law of inertia and other laws of Newtonian mechanics. A frame of reference moving with constant velocity relative to an inertial frame is also inertial, since acceleration of the object in both frames is zero. The velocity of the object is different but uniform. Non-inertial frame. A frame of reference is non-inertial frame. A frame of reference is said to be non-inertial when the objects in this frame do not obey Newton's law of inertia or Newton's laws of motion. In non-inertial frame, every object acted upon by an external force is accelerated. And the motions are relative terms in physics because they depend on the observer's frame of reference. In Newtonian mechanics, space and time are completely separable, and the transformation connecting the space-time coordinates of a particle are the Galilean transformation. Newtonian relativity is also known as Galilean relativity. According to Newtonian relativity, the laws of physics are same for all observers in inertial frames. This means that fundamental physical principles such as Newton's law of motion apply uniformly to all observers regardless of their relative motion. The topic Galilean transformation. It is a set of equations which transform the coordinates of one inertial frame of reference into another frame of reference. Or Galilean transformation is a method of transforming equivalent quantities such as position, velocity from one inertial frame of reference to another inertial frame of reference. Let S and S prime be two inertial frames. Let S be at rest and S prime moving with uniform velocity v along the positive x direction. We assume that velocity of the system far less than velocity of light. Let S and S prime be two inertial frames. Let S be at rest, S prime moving with uniform velocity v along the positive x direction. We assume that v far less than c. Let the origin of the two frames coincide at t equal to 0. Suppose some event occurs at the point P. The observer in frame S determines the position of the event by the coordinate x, y, z and t. The observers in frame S prime determines the position of the event by the coordinate x prime, y prime, z prime and t. There is no relative motion between S and S prime along the axis of y and z well. Hence we have y equal to y prime and z equal to z prime. Then the time proceeds at the same rate in both frames. That is t equal to t prime equal to 0. The distance moved by s prime in the positive x direction in time t equal to vt. So the x coordinates of the two frames differ by the terms vt. Hence x prime equal to x minus vt. And the transformation equations from s to s prime are given by x prime equal to x minus vt, y prime equal to y, z prime equal to z, t prime equal to t. The above equations are known as Galilean transformations. Inverse Galilean transformation can be expressed as x equal to x prime plus vt, y equal to y prime, z equal to z prime, t equal to t prime. Galilean transformation for velocity can be written as ux prime equal to ux minus v, uy prime equal to uy, uz prime equal to uz. The acceleration components can be obtained by differentiating velocity equation with respect to time. Therefore, a prime equal to a. The acceleration is same in both s and s primes. So acceleration and force are invariant in classical physics. Drawbacks of Galilean transformation. The laws of electromagnetism or electrodynamics and the Maxwell equations are not invariant under Galilean transformation. Galilean transformations are invalid when the objects are moving with nearer velocity of light. Now we are going to discuss about postulates of special theory of relativity. An extension of the principle of relativity to the fields of electrodynamics, optics, demands the constancy of speed of light in vacuum in all inertial systems. This fact is verified by negative result of Michelson-Morley experiments. In 1905, Einstein explained the special theory of relativity, which makes a conceptual change in the ideas of space and time. According to Newtonian mechanics, time and space are invariant for all observers, while both are variable at high speed for various observers in special theory of relativity. The two important fundamental postulates of special theory of relativity: all the laws of physics have the same form in all inertial systems, moving with constant velocity relative to one another. This postulate is just the principle of relativity. The second postulate is the speed of light is constant in vacuum in every inertial frame system. This postulate is an experimental fact and asserts that speed of light does not depend on the direction of propagation in vacuum and relative velocity of the source and observer. In fact, second postulate is contained in the first because it predicts the speed of light said to be constant of nature. Expression for Lorentz transformation equations. The Lorentz transformation equations are set of equations in Einstein's special theory of relativity that describe how space and time coordinates of events in one inertial frame are related to those in another inertial frame moving at constant relative velocity. These equations were formulated by Lorentz and later incorporated into Albert Einstein's theory. Let there be two inertial systems, S and S prime. The latter moving with velocity v relative to former along positive direction of x-axis. Let there be two observers O and O prime situated at the origin of S and S prime respectively. Let us further suppose that a light signal spread out from the origin at t equal to 0. When the signal reaches at P, let the position and the times measured by observer O and O prime be x, y, z, t and x prime, y prime, z prime and t prime respectively. The light pulse produced at t equal to 0 will spread out as a sphere whose radius will increase with speed c. Then the equation of spherical surface when the pulse reaches at P relative to O will be x square plus y square plus z square equal to c square t square, or x square plus y square plus z square minus c square t square equal to 0. Similarly, the equation of spherical surface relative to O prime is x prime square plus y prime square plus z prime square equal to c square t prime square. X prime square plus y prime square plus z prime square minus c square t prime square equal to 0. C is not prime since according to second postulate it is constant both since c square a square b into xt minus a square minus k square b square by c square into c square t square. Equating the coefficients of corresponding terms in equations k square minus c square a square b square equal to 1, k square b minus c square a square b equal to 0, a square minus k square b square by c square equal to 1. Solving these three equations, we get values for k, a and b. K equal to a equal to 1 by square root of 1 minus v square by c square. Then b equal to b by c square. Substituting these values of k, a and b in our equation, we get x prime equal to x minus vt by square root of 1 minus v square by c square and t prime equal to t minus vx by c square divided by square root of 1 minus v square by c square. Therefore, Lorentz transformation equations are x prime equal to x minus vt by square root of 1 minus v square by c square, y prime equal to y, z prime equal to z, t prime equal to t minus vx by c square divided by square root of 1 minus v square by c square. Thus, inverse Lorentz transformation equations are obtained by interchanging the coordinates and replacing v by minus v in the above equations. X equal to x prime plus vt prime divided by square root of 1 minus v square by c square, y equal to y prime, z equal to z prime and t equal to t prime plus vx prime by c square divided by square root of 1 minus v square by c square. These equations convert measurements made in prime s prime into those in prime s. Now we discuss the consequences of Lorentz transformations regarding the length of the body and time interval between two events. First we see length contraction. Now we discuss the consequences of Lorentz transformations regarding the length of the body and time interval between two events. First we see length contraction. In order to measure the length of an object in motion relative to an observer, the position of the two endpoints must be recorded. must be recorded simultaneously. Consider two coordinate system S and S prime with their x-axis coinciding at time t equal to 0. S prime moving with uniform relative velocity v with respect to S in the positive x direction. Imagine a rod AB at rest relative to S prime. Let x1 prime and x2 prime be the coordinates of the ends of the rod at any instant of time in S prime. Then L0 equal to x2 prime minus x1 prime, where L0 is the proper length. The proper length of an object is the length determined by an observer at rest with respect to the object. In the above case, L0 is the proper length. Similarly, let x1 x2 be the coordinates of the ends of the rod at the same instant of time in S. Then L equal to x2 minus x1. L is the length of the rod measured relative to S. According to Lorentz transformations, x2 prime equal to x2 minus vt divided by square root of 1 minus v square by c square. x1 prime equal to x1 minus vt by square root of 1 minus v square by c square. Subtracting these two equations, we get x2 prime minus x1 prime equal to x2 minus x1 divided by square root of 1 minus v square by c square. x2 prime minus x1 prime as L0. x2 minus x1 as L. Therefore, L0 equal to L divided by square root of 1 minus v square by c square, or L equal to L0 into square root of 1 minus v square by c square. We see that L is less than L0. Therefore, to the observer in S, it would appear that the length of the rod has contracted by the factor square root of 1 minus v square by c square. For example, a body which appears to be spherical to an observer at rest relative to it, it will be appear to an oblate spheroid to a moving observer. Similarly, a square and a circle in one appear to observer in the other to be a rectangle and an ellipse respectively. The shortening or contraction in the length of an object along its direction of motion is known as Lorentz contraction. There is no contraction in a direction perpendicular to the direction of motion. The contraction becomes appreciable only when v equal to c. The contraction is reciprocal, that is, if two identical rods are at rest, one in S and other in S prime, each of the observers finds the other is shorter than the rod of his own system. Time dilation. Let a frame S prime moving along x-axis with a velocity v relative to. Now assume a gun placed at the position in S prime. Suppose it fires two shots at times t1 prime and t2 prime measured with respect to S prime. In S prime, the clock is at rest relative to the observer. The time interval measured by a clock at rest relative to the observer is called proper time interval. Hence, t0 equal to t2 prime minus t1 prime is the time interval between two shots for the observer in S prime. Since the gun is fixed in S prime, it has a relative velocity with respect to S in the direction of the positive x-axis. Let t equal to t2 minus t1 represent the time interval between two shots as measured by an observer in S. From inverse Lorentz transformations, we have t1 equal to t1 prime plus vx prime by c square divided by square root of 1 minus v square by c square, and t2 equal to t2 prime plus vx prime by c square divided by square root of 1 minus v square by c square. Subtracting these two equations, t1 equal to t2 prime minus t1 prime divided by square root of 1 minus v square by c square, or t equal to t0 by square root of 1 minus v square by c square. Thus, or t is greater than t0. Thus, the time interval between two events occurring at a given point in the moving frame S prime appears to be longer to the observer in the stationary frame in S. That is, a stationary clock measures a longer time interval between the events occurring in a moving frame of reference than a clock in the moving frame. This effect is called time dilation. Now we discuss relativity of simultaneity. The relativity of simultaneity is a concept from Einstein's special theory of relativity, which states that the order of events can be different for two observers in relative motion. This means that when one observer considers simultaneous may not be simultaneous for another observer moving relative to the first. For example, consider two events, the explosion of a pair of time bombs that occur at the same time to an observer who in a reference frame S. If the two events occur at different locations x1 and x2, consider another observer O prime in S prime moving with uniform speed v with respect to S in the positive x direction. To O prime, the explosion at x1 and t0 occurs at the time t1 prime equal to t0 minus v by c square into x1 divided by square root of 1 minus v square by c square. The explosion at x2 at t0 occurs at the time t2 prime equal to t0 minus v by c square into x2 divided by square root of 1 minus v square by c square. Therefore, the time interval between two events as measured by the observer O prime is t2 prime minus t1 prime equal to v by c square into x1 minus x2 divided by square root of 1 minus v square by c square. This is not zero. This indicates that two events at x1 and x2 which are simultaneous to the observer in S do not appear to the observer in S prime. Therefore, the concept of simultaneity has only a relative, not an absolute meaning. Finally, I conclude this chapter. The Lorentz transformations are essentially for accurately describing the behavior of objects at speeds close to the speed of light and are a fundamental component of Einstein's special theory of relativity. Its results and consequences have been confirmed through numerous experiments and have led to advancement in physics, engineering and technology. In contrast, Galilean transformations are a simpler approximation suitable for everyday non-relativistic situations. Thank you.